Okay, now let's talk about that bit. Okay, so if you look here, I am writing a title, a subtitle in red, which says uniform wear, and beside it, between two parentheses, I am saying that this is an old clutch. So why an old clutch? Well, if you read the sentence below, it says that after initial wear has taken place, which we talked about in a minute, just we said that there is an initial wear that can happen right on the top layer because the velocity there is way more than the bottom layer, and that's why friction is more. And assuming that the whole disk is rigid, then you can't do anything about it. So the disk have worn down to a point where uniform wear is established. Why? So the pressure will change until, that's what we said, the pressure will change and adjust until we maintain that uniform wear condition. So in another word, that uniform wear problem is actually never start from the beginning. So if this is a new clutch, it is never starting from the beginning. While as we're going to see, if we put a uniform pressure, those little spring will adjust, and from the beginning, you will maintain a uniform pressure problem. So, so what happens here is this. We will always think of a uniform wear as an old problem, or the clutch involved is old, because we are trying to give you the impression here that what happened first, that early initial wear happened, and then the pressure adjusted itself in order to maintain a uniform wear condition. So if that's the case, the axial wear can be expressed by, this is a wear equation similar to the one we talked about in chapter 12. So we have a wear which is equal to F1, F2, there are two constant or factors, multiplied by K, which is wear factor related to the material itself. Then we have the pressure multiplied by the velocity multiplied by time. Now what you need to understand is that the pressure, P, and the velocity will vary along the wear area. It makes a lot of sense. If omega, which is the angular velocity of the disk, is constant, we know that V, we know that V is equal to omega R. And since omega is constant, the only reason why V is different is because of R. So what are we going to do? We know that in our problem, as we said before, it's like an annulus, and we have a radius here. This is this radius R comes from D over 2. And we have a bigger radius over there, which comes from D capital over 2. And by the way, if you go look at the integration equation in the book, you will see that you will always set the limit for the integral from D small over 2 to D capital over 2. Why? Because you will cover all of this area, right? Now, so then you would imagine that velocity will be maximum on the top over here. And in order to maintain, by the way, that BV is constant, in order to maintain that BV is constant, the multiplication is constant, not B, not V. Their multiplication is constant. So one of them will go up, will increase, and then the other will go down, and vice versa. Is that right? So if we understand that V is equals to omega R, which I just said, and then we express the pressure P as, the applied pressure, which we call it in this chapter, we called it P. By the way, we're just gonna put it P, but in the end, we will be more interested in the maximum pressure, which is usually written as P small sub A. So BV can be substituted P capital by small p, and velocity can be substituted by omega r. Remember, BV here is constant, so we call it C1. This one is also constant. We just, to make it different, we said this is C2. And then we know that omega is constant for the entire disk. So if we divide by omega, we will have a different expression, which is PR, and we call that a new constant C3. Now, we're interested in the maximum pressure because this is where we said that we want to know what is the force to produce that maximum pressure. So we'll put just P maximum, and knowing that P maximum will likely to happen in the location of R minimum. R minimum, the minimum radius is right there at d small over 2 at the inner radius, not the outer radius. So we'll call it Ri, the inner radius. The inner radius is d small over 2. And P maximum, we call it Pa. And that's how we arrive to this relation. Yeah. So PR equals to PA multiplied by D small over 2. Okay, now this expression is very important because we use it in the integration, okay, in order to find the relation for force and torque. Remember, that's what we want, two, force and torque. So um, without going into the derivation as I expressed earlier, we have here the I'm giving you the final expression for F, the force, which is the actuating force, which will which will generate the maximum pressure PA. Remember, this maximum pressure is the maximum that the frictional material can take. So it is by PAD divided by 2 multiplied by the difference between the outer diameter D and the inner diameter small d. Okay? The torque can be found by using this equation by this F is the coefficient of friction for the frictional material multiplied by the maximum pressure by D small over 8, and then we have the squared difference between the outer diameter minus the inner diameter. Now you can express this torque as force by distance, right? So using that, you combine this equation, you can have an expression for the torque, which is equal to F, which is the force, multiplied by the friction, divided by 4, multiplied by D plus capital plus D small. There is one note though. These forces, ya shabab, the force, the torque, okay, in maybe I haven't shown you this, it is already in the book. In the beginning, of the industry and so on, people used in a, let's say, excessive way, the idea of one single clutch, two disc being engaged, and then this is how you transfer the motion. But then they realize that there is a better way. It is maybe complex in terms of mechanism, but it is much more convenient in terms of heat generation and speed and so on, which is making multiple discs, and then each one is stacked with each other. For that reason, this note is very important. These two equations are applicable for single or multiple disks. But if you express this relation here, then it is only for single friction surface. So if there are multiple one, you need to multiply by the number of these. So the amount of torque that you need for multiple one should be T multiplied by those number of single surface. That's why this note is there. So I want you to understand this very well. Now, so I bet you now think about, though, what is the uniform pressure problem then? Well, with the uniform pressure problem, we can have these springs, as we said in the introduction, adjusting themselves in order to maintain as a constant pressure condition. And with that, we tend to think that a uniform pressure problem is applicable to a new clutch case. That's the story behind old and new. So again, if you assume a uniform pressure this time, not uniform wear, you will end up with an expression for the force, which is this. Okay? A little bit different than the other one, right? In the first one, the uniform wear, we don't have d capital square, we don't have minus d square, and then we have pi pa over 4. The torque here is a quadratic form. In a quadratic form, we have d cube capital minus d cube small. And then we have pi f, the friction, multiplied by pa over 12. Again, again, if you combine these together, to find an expression for the torque as a function of the force, you will end up with this equation. This equation has the same story as the previous one. It is only applicable for a single friction surface. If you have multiple surfaces, you need to multiply by the number of those surfaces. You understand? Okay. Now, there is one thing that we would like you to understand over here. Maybe I should have, I should have not have this here. I should not have this over there. Now, if we go to this equation over here, look at it. This equation, I'm gonna clean it, and I just want you to understand it very well. So if I go to this equation, okay, and then divide the torque by this F, and also divide it by capital D. You understand? So you will end up with an expression on the right hand side. Similarly, if you go to this equation, okay, and you have T and you divide it by F, and then you have F, and also you divide it by D, okay, and you will have another expression. These two expressions are shown here. So look, this is the torque divided by F, which is the friction, F is the force, and then D is the capital, the outer diameter, and then the same one. This is like a dimensionless factor, okay? And it is being represented over here. Now, as you remember, we said that a uniform wear is for an old clutch, and uniform pressure is for a new one. So if you look over here, if you look that this factor, as it changes with respect to d small over d capital, it says that you see that the curves seems to be a little bit different in the beginning, but then at one point over here, which is nearly zero point 0.6, they become very similar. So what do we say here? We say that a new clutch always transmit more torque than an old clutch. But for good design, D small over D capital, okay, which is greater than 0.6, the maximum difference is about 2% at D small over D capital D, which is 0.6. So what is the story over here? It says that if you make a clutch, okay, such that the inner diameter, okay, ratio with respect to the bigger diameter, such that that ratio is greater than 0.6, then the difference between a new and old as a clutch transmitting torque transmission power or capability become less than this, which means although you are operating the clutch and there is wear, but you are still maintaining substantially very close torque to compare to a new one, which is great. That's what you want, right? You want it always to maintain its capacity. So this is a very interesting recommendation. All right, ya shabab? Okay. Now, so I told you that we are going to cover also um, um, the cone clutch, okay, and brake. Cone, this mechanism of cone geometry can be used for clutching, okay, and can be used also for for braking. So you can use it for either case. And if you look here, just to give you a little idea over here, what do we have? We have a cup over here. So a cup, which is, geometry has, you know, um, it's divergent geometry such that the cone, which is right there, which is convergent, okay, with a cone angle of alpha. Of course, both of them will have the same alpha. And there is a spring mechanism. So that spring mechanism pushes the cone. The cone will go inside um, the cup, and there it is. This is the frictional material right there. So you can imagine that the friction will lock these together, and then you will have a transmission of load or motion. And if this is a brake, then you can imagine that as you push more, these surfaces will keep sliding against each other, and then the energy, the kinetic energy, will be dissipated in form of heat. Now, just to tell you that the as a literature, or as a nomenclature, I mean, we will have a force pushing the cone, and then here an outer diameter, capital D, a small diameter, a cone angle, and then this is the projection of the force, which is, that force. If you multiply, that force is basically the pressure over a differential area dA. Correct? That differential, what are we going to do? We're going to take a little strip. That strip, okay, has a width, a size over here, which is dr over sine alpha. These are very important when you construct the integral, right? So again, I am not going to go over the integration, ya shabab, but rather I want to show you the the way how we basically derived it. And so we come back again to the same issue. Do we have a uniform wear problem? And what are the corresponding forces and torques? And what happens when we have a uniform pressure problem? So for uniform wear, the pressure relation is the same as for axial clutch. If you recall, ya shabab, we said for axial clutch, PR equals to PAD over 2. That's what we said, right? So here we're just expressing it as a P. So we divide by R over there. That's it. So it is the same. Of course, I am trying here to point for you, because this is an inclined surface, that we have an area dA, differential area, we have a radius r, and we have a width for this differential area, which is dr over sine alpha. So the area itself, dA, is expressed as this. Now, if you integrate to get the force, because the force is the pressure by the area. So when you just put the P, and then you assume that the pressure is reaching to the maximum pressure PA, all what you need to do is to differentiate with respect to dr, right? Such that you will go from the inner radius all the way to the maximum radius. That's it, right? So when you do the integration and you solve it, you will end up with the force is equal to this. Now look at it carefully, ya shabab. It's a pi PAD divided by 2 multiplied by D capital minus D small. This is exactly the same force as for the axial clutch. You see that? So it's the same. So the actuating force to maintain the maximum pressure is the same for axial, right? The same as we did it. That one was a flat surface. This is here, this is the same. And they are both axial, by the way. But the first one, we had just a disk. So this turns out to be the same, the actuating force. Now, how about the torque then? We said because we have a torque, we have a force. So the torque is, this is the expression for the torque. And if you integrate, you will end up with this equation. Now, this is different. right? It's not the same. So what do we have here? It's not the same like the torque equation actually in here. If you look now, look, it is by F P A D divided by 8 sine alpha multiplied by D square minus D square. Now, if you look carefully, you will see that the torque, look at this comment in red, the torque equation for axial clutch, the one we did before. Let me take you to it, okay? All right, where is it? For axial clutch under uniform wear. Uniform wear. This is it. Look at it, ya shabab. It's almost the same. Yeah, there is only one thing which is missing in this one, the sine alpha. So, in reality, what is happening right there is that this is a special case. That one is a special case, I mean, of this one. This is more general case for a for an inclined surface. And if you substitute alpha equals to 90, you will get that one. Do you see that? You will get the same one as the one we did for a flat surface. All right. So again, if we combine this force equation with this torque equation, we will get an expression for a torque force relationship, right? Like a torque equals to a force by distance, kind of. And I bet, although I didn't put the note here, I bet that this is, well, in this one, I don't think there are multiple surfaces. There's not like, multiple disk. So I doubt that this is applicable, similar to the flat one where they are stacked and you need to multiply by the number of surfaces if there are multiple ones. Okay, ya shabab? Good. Now, again, the question is, let's repeat the same issue, right? Let's do the cone with uniform pressure. Now, here, this is definitely a typing mistake. This is supposed to be a uniform pressure. So I will try to adjust this, inshallah, in the slide. So if this is a uniform pressure, then we are going to take the pressure as the P maximum, and which is PA, all right? And the expressions for the force is going to be this, and for the torque, it's going to be this. Once again, this is for uniform pressure. Once again, if you combine these two, you will get this equation. So there isn't much to say here except that you need to understand that for flat axial clutches and brakes, we have a uniform wear expression for the torque and force. We have a uniform pressure expressions for the torque and force. For the cone, you have uniform pressure, uniform wear. And always, whenever you have one condition, you need to find what is the force and what is the torque. That's it. Okay. And I think, if I'm not mistaken, this is where we ended. No, there is one little slide that I need to talk about. Now, if you go back to the equations, this one, let me highlight it again. If you go back to this equation, all right, and then do what? Then say, okay, I am gonna take this, put it down, and then try to take D as a common factor out of it, and go to the other equation, and also take this F over friction and then take this as a common factor. You will end up with the same expression, same story, dimensionless expression. And be careful. This is not for cone. This is not for cone. No. Because in the book, there is no curve for cone. But the two expressions are provided. There they are, Actually, we needed to take sine alpha out. So you'll end up with T here, T sine alpha over F friction, F force, D. And then we have again the same expression on the left hand side. The two expressions are different on the right hand side. So the expectation again is that if you make a plot for the left hand side, so you put T sine alpha divided by F D, and then here you plot D over D. You will get two curves like this, and it will appear, this is what is said in the book, that there is a point which is, it wasn't explained in the book, but I assume it is around zero point 0.6, similar case, where both the uniform pressure and the uniform wear will be almost the same. And that is good for design. So for design purpose, you will go as a designer and you will try to maintain a D over D, a D small over D, which is around this number or a little bit beyond, just to maintain that the the amount of torque transmitted, or the torque capacity for both, is always or very, very close, whether it is new or old. Okay, Shabab. That's it. I'm gonna stop the recording right now, and inshallah, the last recording we will make is for two important subjects. We've been talking about clutches and brakes. There is a huge amount of friction. So the next question would be, what is the temperature? What is the energy generated, which is going to be converted into heat? And how can I know that the temperature will not elevate to a severe limit where the frictional material will no longer function very well? So this is the subject of the last topic of chapter 16. Thank you so much, Shabab.